Okay, testing. All right, there we go. All right, so let's get started. The title is Action Movie Crypto. So what we're going to do is very elementary cryptography, and we're going to move at about the speed at which a summer blockbuster goes. So if you want to lean back and just watch stuff explode, that's perfectly okay. If you know crypto, I'm probably not going to do anything you don't know, but I might do it differently. So, all right, so I'm getting a lot of feedback. Do we have, Jay, can you see if there's a volume to, or maybe there's one here. So what can we do in 45 minutes? Okay, so we can think about crypto at about 3 levels of abstraction. So first we have algorithms, which you're writing algorithms, you're trying to break them, implement them. We can't do anything at that level, except that I'm going to try to do a little bit about the fact that most of us programmers, we don't really know what we don't know, and that's all I'm going to try to do. So at the next level up, the algorithms are actually implemented for us. They're functions in a library. They're black boxes. But what we do is they become like Lego bricks, and we put them together. We call them cryptographic primitives. We put them together into the highest level of abstraction, which is complete cryptosystems. So mainly we're going to just look at the complete cryptosystem level, but we'll play a little bit at this level, partly to give you just an idea of what it means, and also because unfortunately a lot of popular libraries don't actually give you complete cryptosystems. They give you a bag of building blocks and say, here, put it together, which is a lot of exploits come from that. At least you should be a little bit aware of it. All right, the one problem, Jay, is there any way to get the feedback down? I don't think I have a volume control. That I'm ringing in my own ears. So the one problem with doing it this way is if you start at the high level, but you haven't actually studied in the algorithms, it's very abstract. So what I'm going to do is I'm going to actually use some very simple toy cryptosystems to give you a concrete picture, and then what we're actually talking about are things that are algorithm independent, so that doesn't matter. The other thing is we'll get some concepts and some ideas that will help you if you read further. So turns out that we can do everything that I'm going to need with one of the oldest and simplest of all ciphers. We're just going to do variations on the Caesar cipher. So in somewhat modern language, we're going to say this is 2 functions, E and D for encrypt and decrypt. And these are just functions on strings. Functions are little machines, and we put in a string, we just turn the crank, and out comes another string. Okay? Now, I'm not going to try to really define cryptosystems. That's way outside the scope of this talk. But it's pretty clear that whatever we mean by a cryptosystem, D has to decrypt whatever E encrypts. So that's what this basically means. All right? Now, in order to actually present the algorithms, here we go. In order to actually present the algorithm, I have to give you an encoding. So we'll use the simplest one possible, A equals 0, B equals 1, through Z equals 25, in which case the functions are really easy. I'm just taking each letter and adding 3 to encrypt it and then subtracting it back out. The only thing is there's that little mod 26. And if you don't know what that means, it just means when you go outside the range, you wrap it. So if you've ever played asteroids, the coordinates of the ship were done in modular arithmetic modulo the screen size. So if you understand asteroids, you understand everything you need to know about that. All right? Now, first of all, you might ask, is this any good? And the answer is heavens no. Okay? There's no useful security in this algorithm, but that doesn't matter because we're actually using it as a model to stand in for algorithms that you can't attack so easily. So we just don't attack the algorithm in this talk. We just talk about everything around it, everything else. All right? And you just have to trust me, or you can go read about algorithms that actually are secure. Now, there is, however, a different problem with this, with my model, and that's that E and D are the wrong kind of function. So one of the themes of this talk, every cryptosystem involves a decryption secret, okay? And it's that knowing that secret is what makes it easy rather than hard to decrypt a ciphertext. But the only room in that model was for the secret to be the algorithm D. And one of the lessons of history is that that is an exceptionally bad idea. Why is it a bad idea? It's a bad idea because algorithms mean something. Okay, they're hard to find, they're hard to devise, they take a long time to test and gain confidence. You can't change them. Now, we actually want to change secrets automatically every time we connect to a and the real reason is because the purpose of cryptography is so I can order Thai curry over the internet, okay, basically. I mean, you guys may have your agenda, but that's what I want. And that means I'm going to have to actually generate a secret every time I do this. And so it cannot be a function. It cannot be an algorithm. So in mathematical language, it means that cryptographic secrets need to be arbitrary. Okay? They have no significance except we chose them. Fortunately, there's actually something arbitrary in the Caesar cipher itself, and that's the number 3. I didn't have to add and subtract 3. Okay? So what I'm going to do here is I'm actually going to grab that number 3. I'm going to yank it out and stick it up in the argument list. Okay? So, and then that thing we pass in is the only secret we're going to have. Okay? The algorithms are not going to be secret. We call them keys because if you think about it, a physical key, what is its significance? It's actually not worth anything on its own. Its worth is the other things that it protects, the value of what it protects. And that's the only significance to a cryptographic key. So everybody raise your hand, take the oath. I swear my key is a secret, the whole secret, and nothing but the secret. And that's what it means to be a cryptographic key. Okay? So you're all sworn now. All right. So here's what happens when we improve the Caesar cipher. They're just functions like before, but they also take a key. And then to encrypt and decrypt, we simply add and then subtract this key out, modulo 26. And then to decrypt, we have to use the same key to decrypt that we used to encrypt. Okay, so that's pretty straightforward. Now, there is one interesting feature of this model, and that's that 0 doesn't actually encrypt anything, does it? Okay, it has a weak key, but real-world systems actually do a weak key. That's a flaw because it means the key does mean a little bit, but it's a very tractable one. We just make sure we never generate the key 0, okay? But that actually makes an important point, which is that key generation is actually a part of your total security package, even if it's not exactly part of the crypto system, all right? Now you might ask, well, now is it secure? And the answer is, well, absolutely not. It's no better than before. But we don't care about direct attack, but it does have a different, but now imagine a different kind of attack. So suppose the attacker takes some intercepted cipher text, okay, he's watching me and waiting till I order curry. And what he does is he takes a decryption algorithm and he just puts the cipher text in the decryption algorithm and he just starts trying keys one by one, okay? Now, he can do that because we've already taken the oath, algorithms are not secrets, right? So he knows this algorithm. And I got bad news for you. This always works, always. Well, the really bad news is it works against every practical cipher, okay? It doesn't matter who it is, it doesn't matter if the NSA designed it, it always works. Which brings up the rather disturbing question whether we actually have any secure ciphers at all, okay? Now, but fortunately we do. The problem here is that we ask for too much. We ask for security effectively against every conceivable attacker, and that's silly. If God wants to break your cipher, his computer will break your cipher, okay? But we have to lower our sights. So we're only going to ask for security against realistic attackers, and specifically, what is realistic is actually going to be an input into our security analysis, okay? So we have to say so, and then any security proofs that we have, they only apply against attackers we've considered, okay? All right, so what do we have to provide for a model attacker? Well, we have to say how much computing power he has. We have to say how much time he can use it. So one way to think about that is, well, how long do my secrets really need to be secret? We're not that concerned with keeping Charlemagne's secrets secret anymore, although I'm sure they were important to him. So there's a time limit on secrets, and we have to accept that. And any other capabilities that we need. You know, can he make a chosen plain text attack, which is, you know. All right, so we're only using a toy cipher, so we might as well just give the attacker a toy computer. So it'll just be me with pencil and paper, okay? And how long does he have? Well, I'm easily bored, and pretty soon I'm going to think of something more interesting and go, ooh, shiny, and I'll go off and do something else. So it has to get done before I get bored and quit, and any other capabilities I need for the talk, okay? And now we can actually answer the question about the Caesar cipher. It's not secure against our model attacker, and the reason is there's only 26 keys to try. Even I can stay on task long enough to go through 26 keys, right? So we know it's insecure, all right? So let's talk about what went wrong. And what went wrong is actually pretty simple. The key space was too small. You notice it doesn't matter what the algorithm was. We need a cipher with a larger key space if we want security against this attacker. This doesn't apply to any other attacker, right? Okay? And it turns out that we can actually expand this key space on the Caesar cipher, so I can stick with my theme here. So what I can do is I can realize that I don't have to encrypt every letter with the same key. So I could just pick a sequence of keys, like 0, 15, 15, 11, 4, which in our encoding is just the keyword apple, okay? And then what I do is I encrypt the first letter with the first key, the second letter with the second key, till I run out of keys, and then I just repeat it, right? Okay, so it's like 5, in this case, 5 Caesar ciphers shuffled together like a deck of cards, okay? Now, and this has a name. This is called the Vigenère cipher. It's a very famous cipher. And now the question is it secure? Well, against me, because I'm the model attacker, right? Well, so let's just think about that. How many keys are there? There may be, there's over 10 million 5-letter keys. So even if we knew it was 5 letters, I can't possibly try all those. And even if I could, I would get bored and go off and, do something. So it's secure, right? Well, we actually haven't said enough to say, right? What matters is how many keys I'm able to go through. And then the probability of me cracking it is very simple. It's just the number of tries I'm capable of making before I get distracted, and divided by the number of keys, all right? And what does that say? Well, with the Caesar cipher, I can go through all 26. I've got a 100% chance of breaking it, right? Whatever secure means, certain compromise is not it. So we know that's insecure. For Vigenère, my chances are clearly far less than 1, but they're not 0. I could get lucky. I could get lucky on the very first try. So what does that mean? What it means is a couple of things. First of all, we actually can't ask, not only can we not ask for security against any attacker you can imagine, we can't ask for perfect security even against realistic attackers, not with a practical algorithm. So we're going to have to say what level of risk is good enough, what probability is acceptable, and then cryptography can say whether we can achieve it with any given cipher and any given attacker. But it can't be 0, okay? Which brings up the rather fundamental point. Security for cryptography is not absolute, it's probabilistic. You just decide what you want your odds to be, but you're still gambling. You can stack the deck, but you can't stop gambling. And the other thing is, it's kind of an interesting thing. Cryptography is kind of an odd mix of very pure, very theoretical math and very practical considerations. And I kind of find that interesting. So how good is good enough? Well, so if we knew it for the 5-character keyword, maybe I can stick around for 100 tries. Probably not, but maybe I can. So that would maybe my odds of breaking it are 1 in 100,000. Is that good enough? Well, cryptography can't tell you. You tell me. Is it good enough? But actually, it's much worse than that for the attacker, because 5 characters is ridiculous, okay? How about here? Let's take a longer key. 407 years ago, our fathers brought forth in this continent a new nation conceived in liberty and dedicated to the proposition that all men are created equal. Okay, that's a much better key length, and if you take that length, that's an enormous key space. Well, okay, so we're secure, right? Well, here's the problem. I've actually been leading you astray. I'm abusing this cipher terribly, right? So the crypto system's capable of being secure against the model attacker, me. But my key generation is horrible. It's terrible. And we're not going to get the benefit, we're not going to get the security that we could have gotten. And why is that? Well, the keyword apple is an English word. It's not a difficult guess that whoever is doing this is picking English words and not arbitrary strings. So the attacker, if he's any good, will start by actually just iterating through the dictionary. Now, at the outside, if you take every obsolete word, every jargon word you can come up with, you won't get more than 1 million words in English, and you probably get 1/10 of that. So that's already less than 1/10 of what we had just with 5-character keys. And what's worse is that Apple's very common, so it's not a bad guess that whoever did it was a person just picking something that popped into their head. In fact, that's true, that's what I did. So the attacker actually should guess common words first, okay? And so and then you might say, well, all right, but I'll fix it. I'll use a really long key, okay? But I hate to tell you this because you've all been programmed to think that long keys give you more security, but it actually doesn't help, not by itself, because what it really has to do with is probabilities, okay? For example, I gave you a long key, but humans are really bad at choosing keys. That's one of the most famous phrases in the English language. That doesn't sound like something that no one would think of. What's worse is we remember by associative memory. So suppose that was actually protecting the administrative console on a website about Abraham Lincoln. Yeah, you see it. The length is not helping us because it's guessable. So, well, I'll give you the general verses. The optimal attack is just to try the keys in order of probability. So the attacker tries the most probable key. So you should probably start with password and passphrase and key phrase, because that's what people do. And you should try, common proper names and names with a couple of numbers after them. Yeah, you've done that. I know you have. Okay, and let me in. Yeah. Yeah, so there are a lot of ways to do this, but the bottom line is what the attacker is trying to do is to get the most probable key, okay? Now, I actually recommend you try to prove this. It's the easiest security proof ever. It's the only one I could mention at this level, really. Well, except for another. But it's really easy. And this is fair in this attack because this is not an attack on the algorithm. It's attacking the key generation algorithm. Algorithms can't be secrets. So he does know our key generation algorithm. So what went wrong is when I calculated what the probability of breaking it was, that assumes that all keys are equally likely. And I violated that very badly, right? So this is some ancient Greek wisdom from, Euripides or somebody, right? Those are the gods who destroy, they first make to violate the assumptions of their security theorems. You know they said that, right? You believe me? All right. So the point is that what we have to do, so how do we defend against this? This is the other easiest security proof ever. So, get out a pencil and paper and play with it. What you have to do is just satisfy the assumption that I made. Make all keys equally likely. So how do you do that? You generate them randomly, okay, with a uniform probability. All right? So why did I spend time on brute force? Because that's actually the fundamental attack. It's the yardstick we measure everything else by. Because it always works. It has nothing to do with the algorithm whatsoever. And so it becomes key to how we think about security, even when it's not brute force that we're actually talking about. So when I calculate that probability, tries is just about the attacker. It's just about how much effort he expended. Number of keys is just about how much effort it would require. Okay? Nothing else is involved. So the denominator, the number of keys, actually measures the maximum intrinsic security of the system. That's the most we can achieve, right? So what we usually do is we measure this in bits, okay, because it's very easy. So with Caesar, we get less than 5 bits of security, okay? So you're never going to find an attacker that can't do that, right? So with 5-letter keys for Vigenère, you still get less than 24 bits. So by comparison, the original standard, so DES is now deprecated. Why? Well, among other things, it has 56-bit keys, and that was okay when it was devised, but we have faster keys. So Moore's law has destroyed this, essentially. Okay, NIST is now phasing out 80-bit keys, which gives you kind of a measure of where we are in terms of computational power. All right. So the current standard, you actually have multiple key sizes, so you get some adjustable security. My point is just that we use this notion of brute force as a measure, okay? So that's why you need to understand. This is kind of the language of cryptography. The other thing is that you can use this, by comparison, to measure effort for attacks that have nothing to do with brute force, because this is essentially effective security. Now, so Vigenère actually is much worse than I said, because there are actually very effective attacks against it. So you get much less than 24 bits of actual security. So DES has 56-bit keys. I did a little bit of looking. You get less than 3 bits of security with the best known attack. And what does that mean? It just means that with the best known attack, the amount of effort you have to do is equivalent to having to search a 43-bit key space. So it's a very useful yardstick, and it's basically the language we use for cryptography. Now, there are actually a whole bunch of other attacks that are not direct cryptanalysis that are actually kind of fun to think about. We don't have time for them. And most of them don't really fit in this talk because they're really low level. You fix them in the implementation, or they're really high level. You don't fix them with cryptography. You fix them with the rest of your security posture. But there's a couple that I want to talk about. Okay? So let's talk about nature's most perfect food. I usually telecommute. But when I'm in the office, of course, I eat Thai curry for lunch, because science has proven that, along with coffee, Thai curry is one of the few foods that turns directly to executable code in your stomach. So what else would I eat? Yeah. It's science, folks. Don't question it. Okay? Now, obviously, I'm going to order this on the web because the Hackers Union will actually disbar me if I seek out this interpersonal interaction thing. So I have to order it on the web. But what's the form going to have? Well, it's going to have the same name, right? It's Dustin, Laurence, same address, 1410 Abbott Kinney. Very often it's going to be the same order because science has proven that Penang curry and Thai iced tea is nature's most perfect food. And the same credit card number. Yeah, nice try. Sorry. So what does that mean, though? Here's the problem. Every cipher we've looked at encrypts the same plain text as the same ciphertext. It has to. That's what it means to be a function. And that means that somebody, without reading them at all, can correlate ciphertext with real-world events. So, for example, somebody who's watching my highly important web traffic might notice that every time a certain indecipherable ciphertext is sent, 30, 45 minutes later, someone shows up on the street outside of Gem with a bag of curry ready to give it to anybody who looks like they're waiting for it. They can get my curry, okay? I mean, my curry is in danger, okay? So we have to do something about this because fundamentally we have to save my curry. Yeah, forget your problems. All right, so what do we have to do? We actually have to get different ciphertexts when we encrypt the same plain text multiple times, okay? And the functions don't do this unless there's another argument which is varying. So what we're going to do is we're going to actually put another argument in the argument list, which has a lot of names. We'll call it a nonce, and we're going to use a different nonce every time. So here's another hack of the Caesar cipher to make it resistant to this kind of elementary traffic analysis. So they're still going to take a string and a key, and they're going to take this thing called a nonce, all right? And then we just use the key plus the nonce. We offset it, we add and subtract the key plus the nonce, yes? And that means that we have to have yet another version of our little identity, except notice I didn't put the nonce in the argument to the decryption function. Okay, now why is that? The reason for that is basically, remember, we've taken an oath now. The key is the whole secret, so the nonce can't be secret. We are sworn. So what that means is we might as well just send it as the first character of the ciphertext, right? What we've achieved is if the nonce is different from call to call, even if it's the same plain text, it encrypts to a different ciphertext, yes? And that means my curry is safe, which is what I know we all wanted. Now, why did I want to talk about this? It's really too low level for this talk, except a couple of things. Extra arguments in encryption functions shouldn't surprise you. They're there for a reason, but because this is really about how things are put together, I can't give you just a general rule. What I have to tell you is the golden rule of the internet. Read the documentation, okay? Now, I also have to give you a warning. You have to obey it to the letter. You can't decide that you're clever enough to know when you can cut corners, okay? Or don't be Sony, right? Because Sony hard-coded a random number, a random initialization vector, and guess what? Now everybody knows their signing key. When I say to the letter, it means that, you have to keep it unique across reboots. Okay, so if you're persisting, if you have a counter, you're going to have to persist that counter. If you're scaling your web server by running multiple instances, okay, you have a global problem, and you might have to hand out blocks of pre-allocated nonces. You have to actually do it, not kind of, sort of. If it's supposed to be random, which means we probably call it an initialization vector, It has to be cryptographically random. No calling the system rand function, actually for nothing in cryptography. Okay? It means if you had to supply the seed, you're going to have to not use the same seed every time you reboot. I know you weren't going to do that. All right, so now the other thing I think you ought to know about is a very different kind of attack. So let's imagine that I've implemented the Caesar cipher this way. So what am I doing? I'm just for every letter, and this is kind of Python-like pseudocode. For every letter in the plain text, I'm going to add the key, and then if it's outside of my range, I'll just subtract it. I'll just wrap it around, yes? So forget about the fact that every language has a modulus operator, okay? This is a model, right? Now, there's something interesting about this. The value of the key partially determines whether the if block is actually executed, doesn't it? And that's a problem because that means the execution time contains information about the key. So that should bother you. To show you how bad that is, just to make it easy for myself, I'm going to assume that the attacker can make chosen plain text attacks. He can trick me into encrypting messages of his own choice, and he can examine the ciphertext and do whatever he wants. He just doesn't know the key. All right? So he can ask to encrypt a message of all A's. Now, if you think about it, A is 0, so that branch will never be executed. That's the shortest it could possibly take to encrypt a message. So now he can take something in the middle. Maybe it's all ins. Now here's the interesting thing. Whether or not the branch is taken, either every time or never, will control whether it takes the same amount of time as with the A's or longer. And that will tell you which half of the key space the key falls in. And then he can bisect that again. And now you should have a sick feeling in your stomach if you're a programmer. That's binary search. And it runs in log-in time, which means it can actually deal with these enormous key spaces that we try to saddle the attacker with. In fact, you can just recover the key this way. So what's the general thing about side channel? It's incredibly tricky because this is not an attack on the algorithm, even if it looks like it. It's an attack on the implementation. And implementations also mean something, so they can't be secret either, just like algorithms, because we can't change them willy-nilly. There are a lot of side channels. So what does side channel mean? It means basically that there's something about the physical implementation that leaks information on a channel of information that you did not intend as a side effect of the fact that we're doing this in the real world and not in abstract mathematics. There are a lot of them. A lot of instructions will take the same amount of time on a modern processor because it's pipelined and so on, but they'll take different amounts of power because different numbers of transistors are active at any one time. And you can measure that power, okay? You can measure cache timing. Chips give off RF. You have changing currents, which means you have changing electromagnetic fields. So you have RF, and you can measure that, and that's information coming right out of the heart of the processor as it operates. They make sound because those currents heat up and cool down areas of the chip, and then they vibrate because they're expanding and contracting. So this is actually much worse because potentially this is attacking the entire physical implementation. It depends on what code the compiler might generate if you're optimizing, how the CPU is designed and laid out. All right? So what's the lesson here? So those of us that are programmers have no skills. Even though we think we can implement anything, we have no skills in implementing code securely. And the problem is we know so little we don't know what we know, which there's this odd Dunning-Kruger effect which leads to a lot of exploits where programmers implement stuff and they don't know what they're doing because it's too specialized, right? We're actually trained to make side channel vulnerabilities. Why was there a vulnerability that I showed you in my little cartoon vulnerability? It's because I didn't do work that wasn't necessary. I only subtracted if it was necessary. And that creates side channels. So I am trained personally to create side channel attacks, right? I'm a programmer. So the point is, I just wanted to actually give you a reason for the advice that you've probably already heard. Don't go implementing algorithms yourself, even if you know they're perfectly good. That's why you really only use libraries that have been vetted by the community. They've withstood people trying to break them. All right. So here's the interesting thing. At this point, if you believe me that we have algorithms that are resistant to direct attack, we've kind of solved the problems of classical cryptography, which is interesting because there's thousands of years of people not thinking of it the way we're thinking of it. But we have two problems, all right? We have the problem of key exchange and authentication, and these were always there in a sense. But they didn't really seem that bad when we didn't know how to do cryptography at all. Now we know how to do it, and what's left are these, and they're pretty serious. So let's take a look at this. So first of all, let's look at key exchange. So I told you every crypto system requires a decryption secret, yes? Okay. So we have to satisfy this identity, and both the encryptor and the decryptor have to know this secret, right? So that means that you have to communicate the key between two people. And that's kind of a chicken and an egg problem, because you have to do that securely. If you can communicate securely, don't use the cipher. Send your message that way, yes? All right. So what we really do, of course, is in the real world, we prearrange keys sometimes. We're together, we prearrange them, yes? Okay. And that works, sort of, if you're a diplomat or a soldier. You know you're going to communicate securely back with, Washington, with headquarters. It actually doesn't work for us. And in particular, we have the most serious problem. It doesn't let me order curry over the internet. And why is that? Because I can't prearrange keys with every Thai restaurant in every location I might ever visit, can I? It's just ridiculous. You can't prearrange a key with every seller on eBay that you might want to buy something from. You don't even know who they are. You can't do it with every website on the internet. Yeah? Okay, so what that really means is that as we've done it so far, encryption doesn't do what we actually would like to do with encryption. So let's think outside the box for a minute. The problem is that both parties needed the same key. So let's just imagine if we had a more magical crypto system. What if they were different keys? Yes? Now, there's something beautiful about that, because only the decryption key has to be secret. That's why I was very careful to say there has to be a decryption secret. So if I generate a key pair, I keep one of them secret, and then I hand the other one to Dave, and I can just throw it out. Anybody can have it. I'll post it on my website. I'll put it on the MIT key server. And the point is this. So how would that work? So here's an example. There's one more hack on the Caesar cipher, right? So I put public key in scare quotes because this is not really a public key system. But what do we have? Well, first of all, we have three functions. Okay, so we have E and D, which we're familiar with. I put in a new function K. Okay, and it takes something. I'm not going to talk about it, but it's probably just a bag of random numbers. It's going to make a new key pair. Why did I put it into the cipher? There's a reason I'll tell you in a second. What am I going to do? Well, what I've done is I've changed the decryption function. Now it's adding instead of subtracting. That makes it the same as the encryption function, but that's not relevant. That doesn't matter. What really matters is that now a different key has to go. So if you encrypt with 3, you have to decrypt with 23. Yes? So they're different keys. Now, only one has to be secret, so I'll just send the public one, and we got no key exchange problem. Now, you might object, wait a minute, I can easily produce the private key from the public key. And that's true. But this is not a public key system. It's a model. And so for model purposes, you're just not allowed to do that, right? It's a model, okay? And in a real key system, the real reason that you put the key generation algorithm into the set of functions, sort of into the algorithm itself rather than just say pick random numbers, is because now your security proofs have to include the key generation, because this system depends entirely on proving that you are computationally unable to produce the private key from the public key in an amount of time that I'm concerned with. Yes? So you just can't do this, and it's not obvious that any such function, any such system should exist, right? If you ask me, I would say no. That's too much, it's over-constrained. But they do exist, so you'll just have to trust me. But there's another problem, and that's the final thing. This is actually unusable. Why is it unusable? Because it has no authentication. Now, for symmetric ciphers, they actually come with a kind of rough and ready implicit authentication, because the only way to send me an encrypted message is to know this shared secret. So I know I'm communicating with someone with the secret. And if I'm smart, maybe I'll only hand out I'll have a key pair that I hand out to people individually. Yes? And if that is compromised, I have bigger problems than just authentication. But now we're handing it out. And now the entire world can pretend to be whoever they want, and I have no idea. So the matter of fact is we can't use this to do anything, and certainly not e-commerce, which leads to total catastrophe. I can't order curry over the internet, okay? So one more time, we have to save my delivery curry, yes? So we're going to go outside the box one more time. What if I did something crazy and I encrypted something with my private key? Well, I get no security whatsoever. Everyone in the world can decrypt it because I gave it away. But here's the funny thing. Only I can make such messages because only I have the private key, yes? And that's what we want from authentication, which makes one of my final points. The effective notion of identity for cryptography is actually access to a private key. That's the only notion there is. All right? So now I can protect my curry. So let's look at a little model crypto system. What do? So I take my message, my order, I encrypt it with my private key, then I re-encrypt it with the web server's public key. Yes? Now I send it off to the web server. The web server decrypts it with its private key, which proves that we have security. Only the web server can do this. And then it decrypts it with my public key, which proves it actually came from me and not, one of my friends deciding it would be funny to order me 300 orders of curry. No one would do that. All right, so there's only one problem with this. This is the very last thing I really am going to cover. The model isn't quite right, and that's okay because it's a model, except it's not right in a way that you can actually see. If you've ever seen a PGP signed email, what you actually saw was not a message encrypted with a private key. You saw a plain text, and then you saw a little block of data, right? So the fact that it's visible that I'm lying to you is what bothers me, because now you can catch me. So what really happens is that it's surprising that public key systems exist. And while they do exist, we only know of two fundamental schemes, and both of them lead to very slow ciphers. So what we do is we solve this by we use them as little as possible. We use them for the one thing they do that nothing else can do. Okay? But this giving you a better model shows you a picture of what I really mean by putting together primitives. So what do? Well, so what I do is I take the plain text and I hash it. I haven't talked about hash functions. All it means is I have a block of data which can only be produced from the plain text itself, and that's part of the security guarantees of a hash function. So then I encrypt only the hash with my private key. That's this actual signature that you see at the bottom of the PGP message. Then I generate a symmetric session key, right? So that means I need also a secure random number generator. And this is why I said ultimately we're going to have to generate secrets all the time every time we connect to a web page, because I make a session key for a fast cipher. And then I encrypt the plain text and the signature with that symmetric cipher, and then I encrypt only the session key with my public key, because that also is short, and then I send the encrypted session key and the ciphertext. And that's a much closer model to what really happens. Now, so what are the lessons? First of all, public key cryptography solves key exchange and authentication amazingly well. Basically, we do things with cryptography that we didn't imagine doing without them. It's kind of odd that these things are date to the mid-70s? I mean, it's very short, okay? And it just transforms at what you can do. This is the only way to have ubiquitous cryptography, right? Because we're creating crypto world. And that's the only reason we can do it. The other thing is I thought it would be nice to give you a picture of what real systems do, which is to build from many primitives working carefully together and to see what that primitive layer looks like. So I'm done. That's everything I want to say, except since we did a big picture talk, I want to say something about the big picture, okay? And that's that cryptography isn't really about security. It's not even about authentication, and as much as it hurts me, it's not even about letting me order curry on the internet. It's about control of information, and that means that cryptography is not an innocent pursuit, and it's not an apolitical suit. It actually changes balances of power, okay? And what that means is we're creating a cryptographic society, and something I've become convinced of is, so I think this is interesting, you might not, and it's very useful. I get to order my curry, and more importantly, we get to do e-commerce. But actually what it is just some basic literacy, I think, is now a matter of citizenship. Our kids are going to grow up and they're never going to know any other world except crypto world, except the cryptographic society. And that's what we've created, whether or not we want to. All right, we're done. Before we do questions, I want to make one announcement. Right after this, we're going to have a Bitcoin cryptocurrency BOF. It's just down the hall in San Lorenzo B. And Jem has been kind enough to provide some munchies. So, and with that, questions. Yes?
On like edX and Coursera, there are some courses available for like intro to cryptography or cryptography
yes.
courses or whatever. They all mention there's some prerequisite of some kind of math, like probability. Yes. What would you suggest as a fundamental math that you could get learned up on to be able to effectively go deeper into this topic?
The problem is cryptography is very odd. It pulls together actually a number of different things, right? So it's a hard question to answer because it actually covers 3 or 4 fields, including computational theory and number theory, and but it doesn't. It depends on how the course is taught. So the origin of this talk is actually, there's a very good course on Coursera taught by Professor Bonnet, and I thought that was a fantastic course. However, because he keeps it concrete, you do a lot more things with low-level algorithms before you put it together. I'm a top-down guy. My education's in physics. There's a reason I was in physics, theoretical physics, and not, say, observational biology. I want the big picture first, then you can tell me facts if you like. I don't want to know facts until I have a big picture. So I actually gave some thought to first just organizing in my head, and then how do you explain it? Do the simple parts, of which there are quite a few, as you see, without doing all that stuff, okay? So the thing is that I just did it without really much math, but every course is going to be different. The course that Dan Bonnet teaches, it'll ask for some maturity from you. You're going to have to do proofs. And if you've never done proofs, it's kind of not about what kind of math so much as whether you actually are comfortable with real math, with proof and with proofs, basically. But other than that, the problem is there's a bunch of different things, which I mostly had, although my training is actually continuous math. I was in physics, so I have tons of math, which actually is irrelevant for this. But I would say probably more than anything else, if you have some mathematical maturity, if you're comfortable or have once been comfortable and can get up to speed with making proofs, there's a pretty good chance that you can kind of pick up what you need as you go. But I'll tell you the most important thing about online courses. You can drop them at any time. So the real answer is sign up for 3 of them and drop the 2 that are either too low or too high for you. Yeah.
Okay, so with the cipher or any other system where you have a key of 0 and encryption plain text, obviously that's not a good thing. So with your implementation where you add the nonce that with either editor subtract as a key, you also have to build the nonce around the key so that the nonce doesn't cause the key to be 0. So that means that the nonce contains information about the key.
That's true. That's really kind of the reason I didn't say that is that's more or less an artifact of my very, very simple model. So in a real system, that's probably not going to be true at all. Yeah, I mean, no one uses the Caesar cipher for anything but amusement, yeah? Or for teaching a course where you tried to make all the hard parts go away. But I mean, because in fact what I did with the nonce is very, see, I said what I was doing was really below, at a lower level than the talk. So it's really not going to do that. It's going to do something with it. I just gave you a model. However, there are a great many things in cryptography where, think about this. The odds of that happening are something like 1 in 26, right? Yeah. But I only have a key space of 26. What if it was 1 in 100 billion? you might not care. There are a lot of things in cryptography where, yes, formally there's a failure mode, but since we already know that there is a failure mode that somebody might get lucky and brute force it, if it doesn't happen any more often than brute force, we don't care. So you could actually have an algorithm where that could happen, but it's a real algorithm, and it's very unlikely, and then you don't care, because you can't have perfect security. I kept saying, by the way, practical algorithm. There actually is an algorithm that gives you perfect security, it's just not really usable. But go read up on the one-time pad, it's actually quite fun. And there's another talk which would be fun to do, where we point out that, there may be a way to do quantum key exchange and make it work. But anyway, if you think long enough about why the one-time pad works, and I've never really seen a simple explanation, so I spent days working out in my head just exactly. It's actually fascinating, okay? But it's not for this talk. Yeah?
So, I went through all this talk thinking that one of the guns on the projector was broken.
Yeah.
I think it's a furry
I didn't have a Panang colored background. The yellow curry's good too. My wife said, "Are you going to keep that yellow background?" I said, "Well, I don't know. I kind of liked it." But then no one asked me for fashion advice. I don't know why that is. Anybody else?
The other reasonable question I actually had was there are cases where, as you're working through the cipher, you actually get information about failed attempts as you're trying. So, for example, the Caesar cipher, you had with the five, not the Caesar, but the V one, the Frenchy one, right?
Wiesner cipher, yeah.
So you had five, but effectively within one or two or three numbers, you would know that you were off, and then you would
right.
throw that away.
So that's true, and in an early draft I sort of mentioned that, and then I realized that it was just me nattering off on a side tangent. But if you think about it, that's at least partly kind of an attack on the algorithm, because one of the failures of all such ciphers is that every bit of the ciphertext does not depend on every bit of the plain text. And if I'd really given you a good definition of a really good cipher, one of the things we would look for is, I think that's often called the cascade property, if you're sort of putting together iteratively, where you want every bit of the ciphertext to depend on every bit of the plain text, so you actually have to do the whole thing.
The reason I brought that up is because the Enigma machine was partially broken because the machine was designed never to return the encrypted letter to be the same as the original letter. And they could use that.
That's information, isn't it? Yeah.
Break down. Without that flaw, they would have a much bigger problem.
Sure. Well, that's a flaw, but I mean, the thing is, we didn't know how to do cryptography, right? Everything before, I was going to say Claude Shannon, that's not quite fair, but there's a generation of cryptographers that discovered that this is a mathematical discipline, and it's like physics. Nobody who did it without math ever did anything that's secure against anybody who did it with math, and vice versa. It's just a mathematical discipline. But you're right. I mean, all of those historical ciphers have these flaws in them, because what they weren't doing was what Claude Shannon taught us to do, which is to ask, where's the information going here, right? And you're right. I mean, if it never repeats, if it never encrypts, if it always changes the letter, that itself is a piece of information, yeah. Yeah.
So, one of the things about cryptography and trying to convince someone to actually do cryptography is that they have trouble conceptualizing how PKI even works. Like, I have a private key and I'm giving you a public key, and vice versa. Do you have a real world simple analogy that would help in explaining how public and private keys end up interacting?
I guess I could try to concoct one, but I'm not sure I can think of anything sort of natural. You probably almost certainly could construct a physical lock that only turns in one direction with one key and the other direction with the other key. And then you could imagine having a box, right? And just say, well, okay, you could all have a copy of the key that locks it, and I'll just leave the box there in the back. And then, if you want to say anything to me, just put it in there, lock the box, and then, leave it on the table or whatever. And that's probably, I mean, that's obviously close. The only problem is I just invented that. So I don't know if that's entirely fair. Actually, no, here's a better way. Imagine this. So I take a box, it has a hasp on it, and I leave an open padlock next to it. If you want to leave a message for me, put it in there and then click the padlock, because you know you can do that without the key. So the padlock is kind of taking the place of the public key. But you can't unlock it without the key, and I keep that. That's the private key. That's probably the best one. So I guess the answer is yes. I didn't know that. Yeah.
This is sort of a personal nid of mine. Don't get me wrong, that was a great talk. But if you go back to the 1978 Schroeder paper, the actual subject is comparing public key systems and private key systems. And what they actually do is they take all of the standard operations that an enterprise might want to do, like encrypted email, encrypted files, et cetera, and for every single case, they design and present both a public key solution and a private key solution.
Okay.
And compare them. And the conclusion of the paper is basically that the public key versus private key is a red herring.
Well, so I haven't seen the paper, so...
It's a lot easier to
Yeah.
explain authentication with public key systems than private key or symmetric key systems.
Okay.
But the Kerberos authentication system is sort of an existence proof with the fact
Okay.
that you don't have to use public key
Okay.
to authentication.
Well, I mean, I don't know anything about it, so that's kind of interesting. What's the paper?
Schroeder, and I forget what the
Right.
title is, but it's Communications of the ATM, and it's
Okay.
1978.
Interesting. So my first question, being kind of a cynic, is, so my graduate advisor once gave some profound advice that all of us grad students are like, what? He said, never do a calculation until you know the answer. So what that means is that don't get you. So before I try before I read the paper and understand it, my first question would be to find out if I need to read it. Why is it that all of the cryptographically sophisticated entities that I know of actually use public key systems? And I'm not mocking. I'm actually asking seriously. Why is that? Because
There are actually things that you can do with public key systems that you
Yeah.
can't do
Mhm.
with symmetric key systems. It's just that if you go through the obvious standard list of things,
Okay.
they aren't on that list.
Okay.
Now, if you want to embody your authentication in a physical device like a smart card, for instance, and you want it to survive somebody stealing the smart card,
Okay.
then a public key system has some properties that
Okay.
a symmetric key system wouldn't have.
Okay. Well, since those are usually weak computers, it makes me wonder. My second question was, are these actually computationally practical constructions? And again, I'm serious because I don't know the paper. Anyway, in systems that run in exponential time or exponential memory are probably only of theoretical interest. So.
Solutions that they present are less practical.
Okay.
I will say that the majority of them have been cracked since then. In particular, all of the public key solutions that they presented have been cracked.
Okay.
Which I think tells you something about the relative complexity of public key solutions versus symmetric key systems.
Well, we know they're kind of brittle. And that's another reason I didn't say. There are security reasons to minimize how much we use them. There's a nice little paper on Dan Bernstein's website of his discussion of the problems of most of the curves that we use for elliptic curve cryptography. And his general attitude is most of the ones we're using have serious problems, either theoretical or they were almost like they were designed to be very hard to implement correctly. So, not that any of us are paranoid. So, anyway, well, thank you, because I should find that paper, because that's interesting. Yeah.
The reason it works because the keyspace, we over anything else, so you could just truncate random down to the end, and you wouldn't know that you decrypted the message, because you can decrypt any message that the encrypted one through the one-time pad can be decrypted to anything.
Well, so that sentence is actually the real answer. If you have 1K of data, because the key is as long as the data, you can actually map it to any other string of that length, right? And including strings with nulls in them if you have them, which means that you could do brute force. And what you're really doing with brute force, if you don't mind me using a little more language than I did, what you're really doing with brute force is you're taking the ciphertext and saying, what's the pre-image? In other words, what is the whole set of plain text that actually encrypt to this for some key? And then you look at them and you basically say, well, most of these are meaningless, but you're putting in some kind of knowledge, generally. The problem with the one-time pad is that since every possible string could be mapped under some possible key, you can do a brute force attack and you have no information. You have not narrowed anything. You still have the entire space of possible strings. So the jargon is that it's information theoretically secure. There's not enough information in the ciphertext to actually decrypt it without knowing the key. Okay? The only problem, so I said practical. There's a project. Do you remember the name? Anybody remember the name? The Russians actually use the one-time pad a fair amount because there was a project. Yeah, Dallas, Venona. Yeah, you can look at that even just look on Wikipedia. It's actually pretty fascinating because what happens is, as far as I can tell, they did the best job that anybody ever did. Apparently because they were more paranoid than anybody else ever was. Everyone who apparently uses the one-time pad with any frequency ends up accidentally repeating keys or running out of them because they're in the middle of a war and they can't get the books out or something. And it's so brittle that if you repeat them once, then, the ones they never repeated, we never broke because it can't be done, but they could reuse a key once and then we would break them because it's that brittle. This is not something I'm deep into, but I was kind of interested in the subject, and it's actually rather fascinating to read the description of that. So the point is, there is something out there that gives you perfect security. It's just that it requires you to exchange so much key information that in practice you might as well use whatever you exchange the key with. Yeah.
I remember vaguely one of the problems with the Russian one was they would send the weather, and they knew what the original text was at some level.
Yeah.
And the weather would typically repeat itself the same over and over again with different keys, and they could break it that way.
Okay. I don't remember that part of it. I was, at the time when I was looking at this, my biggest interest was in making sure that I really did understand the one-time pad. And so I was kind of looking to make sure that what I had figured out was actually what happened in practice when they used it. But it's fascinating, and I highly recommend. The other thing that's interesting about it, since I was a physicist in a galaxy far away and long ago, there's a possibility that you can actually use quantum mechanics to exchange keys, and then actually it becomes a practical system. And we may be on the verge of doing that. See, who was first? I think you were first.
Could you not look for a group with a one-time pad because the key for that string has no bearing on the key for the rest of the string? You can only different weather.
I'd have to think about it a little bit to have much of an opinion. I don't think it should be compromised with repeated plain text alone because the key should be completely statistically independent every time. So I don't really understand why what you said would be a vulnerability, but again, this is the kind of thing. I'm a programmer, not a cryptographer. I just came to the conclusion once that we're no longer at a point where we can afford to have programmers that don't have some literacy. And that's really why I gave this talk, because I'm not a cryptographer, but we can't afford to not all have some literacy because, guess what? Every one of us that writes code is tempted to do things we shouldn't. So I have to think about these things maybe longer sometimes. Yeah.
Is there a short explanation you could give of why, we're talking about attacks on length of keyspace, and like DES is mathematically weak because 56-bit key.
Yeah.
But triple DES is still something that it's acceptable. It's not as preferred as like AES with a much longer keyspace. But with triple DES, when you re-encrypt, you have your ciphertext
Yeah.
re-encrypt. So a brute force attack, you're going to decrypt it to ciphertext. How are you going to know that you have the correct ciphertext to continue your attack down various levels? Is there a short explanation of why multiple levels of encryption isn't much closer to perfectly secure?
Well, I mean, so you're getting more security because effectively you have like, what is it, 168-bit key. You don't actually get all of that security, but I mean, you do get something. I think, what is it, supposed to be worth about 112 bits of security, I think. Yeah. Oh, it's really slow, yeah. I mean, there's no reason to use triple DES except that some people are either have invested in a lot of stuff, or they're really conservative, and they know they're not getting sued for using what they're doing, and they're not sure yet if AES is. I mean, there are reasons people do this, right? Some of them are not rational, and some of them are rational based on considerations that we don't have. But yeah, I mean, triple DES is crazy to use if you don't have some external reason, because it's horribly slow, and there's a reason that DES is deprecated. Triple DES is a stopgap. Yeah, I mean, it just is. So, I tell you what, I should probably dismiss you guys because I think it's about time for the BOF, but I'll stay, or we can go over to the BOF and talk if you like. But thank you very much. I didn't know if anybody would show up for this. Thanks a lot. Did I keep you awake, Dave?